Stanford University.
We haven't talked much about geometry. We've supposed that space is flat, space. And we haven't even talked about space-time geometry at all this quarter. In fact, as a matter of observation, space is very flat. But it's not a principle. And it's important to understand, very important to understand, what cosmology would be like if space were not flat. And as I've emphasized over and over, it's not that we know that space is flat. We just know it's very big. Whether it's flat, positively curved, or negatively curved, we really don't know. And so it's important to investigate the various possibilities. Now, we don't know a lot on scales of space much larger than 10 billion light years, 20 billion light years. But we will make some assumptions. The assumption will not be that space is flat, but at least for the time being, let's continue to assume that it's homogeneous and isotropic. Is that true? Maybe it's not, but we'll never know until we learn to find out its consequences. And the only way to find out its consequences is to assume it and see what it says. Then we should assume the opposite and see what it says. But because almost all cosmology is based on that assumption, it's a good thing to explore that space is not flat, but homogeneous. Now, what does that mean? Space not being flat means that it's curved. What kind of spaces are curved? Well, a sphere is curved. A paraboloid is curved. An ellipsoid is curved. An ellipsoid with a bump on it is curved. So all kinds of curved surfaces that you can think of. Now I'm thinking about two-dimensional surfaces. We'll come to three-dimensional spaces soon enough. All sorts of spaces you can imagine are curved, but only a very, very small number of possibilities are consistent with homogeneity. Homogeneity means the space is everywhere the same. Somebody located at a particular place in the space looks around him, sees everything around him, and sees exactly the same thing that somebody else sees in any other position. That's called homogeneous. A ellipsoid, or let's start with a paraboloid. A paraboloid is most certainly not homogeneous. It's more curved near the tip of the paraboloid. It's less curved far away. An ellipsoid, a long pointy ellipsoid, is different near the poles of the ellipsoid than it is near the waist of the equator of the ellipsoid. And if you were walking around on it, you would notice the difference. You would notice the difference seriously. You would not be fooled, unless, of course, it was huge and you couldn't sample the curvature. So ellipsoids, spaces with bumps on them, the surface of the Earth, if we take into account the mountains and the valleys on it, are curved surfaces, but they are not homogeneous. Okay. What kind of spaces can be curved and homogeneous? Well, basically, there are only two kinds, two classes. In fact, apart from the size, overall size of them, there are only three kinds. The first kind is flat space. Let's begin by thinking about a metric for space. Not space-time now, just space. The metric of space. Flat space is just good old flat space, right? Flat space is just good old flat space. And if we were talking about two-dimensional flat space, it would mean a plane. And a plane, the distance element, the distance between two neighboring points, we know what it is. It's just dx squared plus dy squared. If we want to add a third dimension, All we have to do is add a third dimension, straightforwardly, dz squared. That's the way we describe spaces, by giving their metric tensor, or giving their metric, the distance between any two neighboring points. If we know that, we know everything about the space. This is ordinary flat space. Okay. You could. We don't, but you could. Okay. All right. Let's think about the two-dimensional example. And instead of working in Cartesian coordinates, let's work in polar coordinates. Polar coordinates have some nice feature when you think about cosmology. They have a center. And if you think of the center as U, they have a natural place to put U. You look around in the sky, you look up into the sky, you look around, you're looking around at angles. Your visual field is a field of angles. If the world was only two-dimensional, then literally looking around you would be looking around at angles, and what you would see in front of you would be laid out in an angular space. So it's useful to think in polar coordinates in cosmology. In the two-dimensional example, we introduce an angle, theta, and a radial variable, r. The usual thing. We've done this over and over. And I think everybody knows the metric. The metric in polar coordinates, the same metric, ds squared, is equal to dr squared, distance radially, plus, not d theta squared, but what? R squared d theta squared. This is just a statement that the distance interval for a given d theta, there's a given d theta, a small angle, gets bigger and bigger and bigger as you move away, and it gets bigger linearly with the distance, but the square of the distance grows quadratically with r squared. So that's the metric of the ordinary plane, and we're going to give it another name. We're going to invent a new term for d theta squared. What is d theta squared? D theta squared itself is a metric. It's a metric for a particular space. It's a metric for a circle. If I had a circle, and incidentally, a circle is a kind of sphere. It's a one-dimensional sphere. It's one-dimensional, you move along it. Somebody living on it would just think they're living on a one-dimensional space. And sometimes a circle is called a one-sphere, meaning to say it's one-dimensional, but it has a topology that closes back on itself. And sometimes the circle is called omega 1. Omega doesn't, I don't know where omega came from, but 1 is just the fact that it's one-dimensional. And we sometimes refer to d theta squared as just d omega 1 squared. It just stands for the metric of a unit circle. D theta squared is the metric of a unit circle of unit radius. When I say unit circle, I mean radius equal to 1. The metric would just be d omega 1 squared. We're going to adopt that notation because it'll occur over and over. We don't always want to have to write the details of a metric, so I have a name for it, d omega 1 squared. Okay. Any questions?
When you say that d theta squared is the metric for a circle, are we saying that it measures the distance along the circumference?
Measures the squared distance of a, yeah, it measures the distance along the circumference, right. Now, it wouldn't make any difference if we took the circle, think of it as a piece of string going around in a circle, and deformed it so that it looked like this. It would still be true that you could still label the circle by the same angular coordinate. Still label it by the same angular coordinate so that equal intervals along equal angular separations, and you would say that the metric of the deformed circle would still be exactly the same thing, d theta squared. So it doesn't matter that you draw it as a circle. The circle is just a space along which, if you go a certain distance, you come back to the same place after a distance. And in this case, the distance would be 2 pi. If you measure in meters, and you lived on a circle, and the circle happened to be have a circumference of 2 pi meters, you would call it a unit circle in the metric system. We'll just think about the abstract unit circle, which has a length around it of 2 pi. But then, when it goes into the polar coordinate metric, each circle has its own radius. The radii increase, and so we put r squared in front of the omega 1 squared. And that's the metric of the flat plane. That's flat space. In this form, it looks like there's a special place, but there isn't a special place. Every place is the same as every other place. It's just we use our place as the center. Now let me draw it on edge, sort of. There's a series of family of circles, and we can think of the flat space as a kind of nested sequence of circles of increasing size. Think of it that way. Think of the flat space as being composed of a nested series of circles, each one having a radius. The circle has a radius equal to its distance from the origin here. All right, next let's go to the sphere. The sphere is also a homogeneous surface. Every place on the surface of a sphere is exactly the same as every other place. So it's not the plane, but it is homogeneous, and let's discuss its metric. Again, now I'm talking about the 2 sphere. We talked about the 1 sphere. That's omega 1. Now we're going to talk about the 2 sphere. The surface of the Earth is a 2 sphere. It's 2-dimensional, and it's a sphere. Okay? A sphere, of course, has a particular meaning, but for us, the main meaning that it has is that it has uniform curvature. It's everywhere the same, and it has the property that if you walk around it, you come back to the same place in any direction. That's the main properties of it that we care about. So let's draw it. Here's the ordinary 2 sphere. And let's also think of it as a sequence of circles. In this case, we're going to start at this point. We're going to call that, here's where we are. I'm right at this point on this sphere. And now I look out at different distances. And what do I see? I see a series of spheres. Nested spheres. I look out. Near me, I see the first sphere. So when I say look out, I mean I'm an astronomer. I'm looking out away from my own position. I happen to be a 2-dimensional astronomer instead of 3 dimensions. And at 1 light year, I see everything arranged on a sphere. At 2 light years, I see everything arranged on another sphere, another sphere, another sphere. But there's something different about this series of nested spheres. And it's that as I move out, instead of growing, the spheres stop growing. They grow more slowly as I move out away from the center here. And eventually I come to a point where the spheres don't grow anymore and then contract. Now this is not with time, this is with distance. The 1 spheres, the circles out of which the 2 spheres are formed, instead of growing linearly with radius, they grow for a while and then they shrink. And in fact, we know how big each one of these spheres is. If the spheres are characterized by an angle, let's call that angle r. R is the distance from this point as measured, let's say, in angle. So r is 0 over here. R is pi over here. That's just a way to label the sphere. That's just a set of coordinates to describe the sphere. Right where we are, that's r equals 0. The furthest we can see until the sphere closes up on itself at the back end, we'll call that r equals pi. Okay. What is the metric of the sphere in terms of r? It looks a lot like this, but slightly different. This is flat. Now, sphere, ds squared equals dr squared. What's the radius of each one of these circles? Do you know? Sine r. Sine r. At this end, where r is equal to 0, sine r is equal to 0. What's sine of pi? Also 0. All right? Sine of pi over 2, here's pi over 2 over here. Pi over 2, pi over 2. On the equator, the radius of each one of these spheres, instead of growing with distance like this, stops growing, comes back, and the answer is sine squared of r, sine squared means the square of the sine, times the metric of a circle, of a unit circle. Instead of r squared, we have sine squared r. We can write d theta squared here if we like. D theta would be the angle around here. All right. But we can also call it the omega 1 squared. Same thing. So let's put the omega 1 squared. All right, so we built, and now, what is this the metric of? It's the metric of the two-sphere. All right, so let's give the two-sphere a new name. The new name of the two-sphere is d omega 2 squared. Omega 2 is a two-sphere. This is omega 2. Omega 1 is the circle. Well, this pattern just continues. If I want to make a three-dimensional sphere, a three-dimensional sphere is a three-dimensional space. Everywhere is the same. If you go out in any direction, you come back to yourself. Think about looking out in the sky again. You look out in the sky, you see things at a certain distance. They form a two-sphere now, not a circle. They form a two-sphere around you. You look a little further, another two-sphere, even bigger. You look a little further, and you see a very big two-sphere. But then what happens if you look a little bit further? The two-sphere starts to get smaller, and smaller, and smaller, and smaller, until you see around to the other side of it, where it shrinks again to a point. Three spheres are just as good a space as two spheres. They're harder to visualize. Your visual cortex doesn't have the machinery to be able to visualize directly three spheres, but they're just as good. And what they are is, instead of a series of nested one spheres, which grow and come back and collapse as you go further and further away, there are a series of nested two spheres. One sphere, another one inside it, and the bigger one, bigger one, bigger one, and then they collapse. So you could think of it then as you move further and further away in R, at first you see a small sphere around you, a small two-sphere around you. Then you see a bigger two-sphere around you. I'll draw it as a two-sphere so that you can see it. And then you see an even bigger one at further distance. And then they start to get smaller again. And where do they shrink to 0? At r equals 0. And again at r equals pi. No, no. The observer is on the sphere. Oh, no. The observer is at this end. This series of spheres here refers to the spheres that you see around you. The spheres that you see around you, the closest one, you know, my head. My head is the smallest sphere around me, right? It's pretty small. That's this one over here. I look out a distance a meter, and I see a bigger sphere. I look out a distance 10 meters, and I see a bigger sphere around me. If I were living on a three-sphere, then I would look out to a distance which would be a biggest two-sphere, and then they would start to shrink again. It's exactly the same thing as here. You see around you a small sphere, you see a bigger one, or a circle, a bigger circle, a bigger one, and then they start to get small. You're over here. So we could have drawn this by saying at this end we have a point, a little bit further away we have a circle, then we have a bigger circle, then we have a bigger circle, and then the circles shrink again. Now in the case of the two-sphere, I can draw it as a sphere, a recognizable sphere, but just think of it as a series of circles which grow and then collapse. And they grow and collapse as a function of r, from r equals 0 to r equals pi. If you want to go another step to three-dimensional spheres, you think of them as a nested series of concentric two spheres around you. Okay, now you should be able to guess what the metric of a three-sphere is. This is the metric of a three-sphere. It's the omega 2 squared equals. Again, there's a dr squared. There's always a dr squared. That's distance away from you. And then there's the angular part. And the angular part now will not involve circles, but the angular part will involve two spheres, a series of two spheres around you. And that will be sine squared r, the omega 2 squared. Not the omega 1 squared, but the omega 2 squared. Here's flat two-dimensional space. What about flat three-dimensional space? Here are these two spaces are spheres. Two spheres and three spheres. This should be d omega 3 squared. The omega 3 squared, which is the three-sphere, and we may be living in on a three-sphere. Possibly we do live on a three-sphere. Space may be a three-dimensional thing like this. All right. This was the easier to imagine analog. Here's flat two-dimensional space. What about flat three-dimensional space? What would you guess? You have a guess for flat three-dimensional space in this form? Yes, you have another angle, and that other angle forms an omega 2 around you. It's just this. Flat three-dimensional space in polar coordinates looks like this, where this is a two-sphere. It just corresponds, again, to the two spheres that, that surround you. Polar coordinates. This is a standard notation to call the metric of a sphere d omega squared. And you put a little index in to indicate how many dimensions it has. There's another way to view spheres. I might as well tell you what it is. It's in some ways a little more intuitive. Well, I'm not sure. Well, I'm not sure it's intuitive. But it requires some extra baggage. A circle, now a circle, if you were a little ant living on the circle, and you couldn't look off the circle, you couldn't look into the circle, all you could do is receive light from along the circle. You could communicate with your neighbors, but you would have no way of telling whether it was truly a circle or whether it was a thing like this, or even if there was no other dimension. Perhaps all there is the space along the line with no sense of moving perpendicular to the line. That's what a creature living on this line who couldn't see off the line, you know, somebody who lived on an optical fiber maybe, who could receive no light except from along the fiber, would have no way of telling whether that fiber in 3 dimensions was truly circular, or if it had some other shape, and maybe wouldn't care, and even more, might actually just be living on the one-dimensional space with no sense of a perpendicular direction. But still, nevertheless, we can, if we like, describe a circle by embedding it in 2 dimensions. It's only one-dimensional, but we can embed it in 2 dimensions. And how do we do that? We write that the circle is x squared plus y squared equals 1. That's the circle, right? Common distance every point, same distance from the origin, namely, in this case, a distance 1. That's the unit circle. The unit 2-sphere, we introduce a 3rd direction. Notice that to describe a 2-sphere in this way, we have no choice but to introduce a fake 3rd dimension. Now, the 3rd dimension in the case of the surface of the Earth is real. You can move in the perpendicular direction. But again, if you thought about a world, flatland, if you thought of flatland where creatures can only receive light from within the surface itself, then the extra dimension would just be a trick for describing the circle, describing the sphere. We would describe it as x squared plus y squared plus z squared equals 1. That's a surface in 3 dimensions, but that surface in its own right is a space, and it does have it has exactly this metric. If we measure distance away from one of the poles, in the same way, the metric of the 2-sphere, this is the 2-sphere, is exactly what I wrote there. Well, you can go another step. You can say, let me construct a 3-sphere. To construct the 3-sphere in this way, you have to embed it in a 4-dimensional space. Again, now the 4-dimensional space may really be a fake. Maybe only the 3-dimensional surface makes any sense. But you would add one more letter. And this surface, this 3-dimensional surface in a 4-dimensional space is the 3-sphere. Again, if you coordinatize it by distance from some point, this is the metric of the 3-sphere. Okay. Embedding it in a higher dimensional space may or may not make real sense. In other words, really have physical significance. As I said, the surface of the Earth is embedded in 3-dimensional space. If we live on a 3-sphere, chances are it is not embedded in the same way in a 4-dimensional space. But we don't have to answer that question. Okay. What's the difference in terms of what you perceive if you live on a sphere versus if you live on an infinite flat plane? How could you tell? Well, let me suppose you had telescopes, and those telescopes allow you to determine the distance to distant objects. Just the distance. In other words, to determine the R of the galaxies which are embedded in your space. A telescope in itself, of course, doesn't allow you to tell the distance, but let's suppose you had some various tricks to be able to tell how far things were away. The standard trick was, of course, spectroscopy, but using the Hubble law. So it's a combination of things. But in this particular case, what could we use as a trick to tell how far a galaxy was away? Could look at its luminosity, how bright it is, right? So we could look at, we just look at how bright it is. You know, how much luminosity we're getting from it. A bulb, a light bulb far away looks less luminous than a light bulb close up. So let's assume we can tell. And let's look at an object, a known object. It's a galaxy. Let's assume all galaxies are the same. This is, of course, not true. But on the average populations of different kinds of galaxies, we can look at a distant galaxy and we can from the type of galaxy. If it's a galaxy like our own, with roughly the same number of stars, we can't really see the individual stars, but nevertheless, if it's a galaxy like our own, we'll assume it has about the same size, 100,000 light years across or whatever. And so we look at these galaxies, we can tell how far they are, and for simplicity, let's just say they're all the same size. And then we can ask, how much angle do they subtend in the sky? Right? We see a galaxy, and obviously, the further away the galaxy is, the smaller the angle it subtends in the sky. You know what subtends means, how big an angle it looks in the sky. So let's begin with the flat space and ask, assume galaxies, all galaxies have a diameter d. This is the diameter of the standard spiral galaxy. Our standard kind of spiral galaxy has diameter d, and we're looking at it from different distances, or it's different distances from us. How big an angle does it subtend? All right, so we look at the metric. Here's the metric. Let's do flat space. Here's flat space. And for simplicity, just take the two-dimensional case. This doesn't matter. We just look along a circle. All right, so there's galaxies out here. Galaxies here, galaxies close by, galaxies very far away. Each galaxy has diameter d, and let's think about the angle that it subtends in the sky. There's the angle that it subtends in the sky. It has size d. D is its true size. So that means that ds squared from here to here is just d squared. On the other hand, it's equal to dr squared. Well, I don't care about r. I'm just looking between here and here. Those 2 points are at the same radial distance. So if I look at this little line or this little surface across here, dr is 0. This is a little line at a fixed r. So dr is 0. Here we are. Is equal to r squared d theta squared. Just this part, where is it? R squared d theta squared. That's for the ordinary flat space, two-dimensional space, 2 dimensions. D squared, the actual size of the galaxy, is d squared. And it's equal to r squared d theta squared. Nothing new there. So what's d theta? D theta is the size of the galaxy divided by r. I've just solved this by writing d theta squared is d squared over r squared and taking the square root. Okay? So the angular size, this is obvious, incidentally. I'm not saying anything you don't know. The angular size in the sky is proportional to the actual size of the galaxy divided by its distance from you. So we could check this. And we can measure the distance to the galaxies. We can see how big they look in the sky. If we lived in flat space, we would discover that the angular size of them decreased like 1 divided by the distance. Now let's do exactly the same thing on the two-sphere. Incidentally, this fact is true in 3 dimensions. It's true in any number of dimensions. But now let's do it on the sphere. And for simplicity, let's just imagine the two-sphere. All right, so here we are. We're over here. And we're looking out at the galaxies, which are all about the same size. They fill the space pretty much homogeneously. We can tell how far they are from us in the same way that we told before. We can measure their angle. Let's see what we get. Again, the size of the galaxy is d squared. And now, instead of being r squared d theta squared, it's sine squared r d theta squared. We look out here. We look at this galaxy over here. The angle subtended satisfies d squared is sine squared r d theta squared, or d theta is equal to the size of a galaxy, not divided by r, but divided by sine of r. What does that mean? Which is bigger at a given distance? Well, sine is smaller than r. R increases linearly. Sine r turns over. So sine is smaller than r. That means d theta is bigger than it would have been in the flat case. The distance to the angle subtended by a galaxy at, let's say, 1,000, a couple of million light years away from us. Let's make it more than that, a few billion light years away from us. If we lived on a sphere, that galaxy would look bigger. It would look bigger because sine r decreases. Well, it doesn't increase as fast as r. In fact, when you get around to the other side of the sphere, where sine of r starts to decrease, the galaxies out here look bigger than the ones in close. Here, I'll take this galaxy over here and compare it to one almost at the antipode, at the other end of the universe. At the other end of the universe, the sine is almost 0 again. So the galaxy over here looks about as big as the galaxy over here. So you could tell. You could tell it would look fainter because it's far away, but or would have whatever properties a distant galaxy is supposed to have. But as I said, if you had a trick to tell how far away it was, you would find something different about the spherical geometry. Namely, up to a point, the distant galaxies would look smaller and smaller in angle, till you got halfway around, and then they would start increasing in size again. In fact, if there was a galaxy right at the antipode here, you would see it in every direction that you look. So you would see it if you look that way, you would see it if you look that way, you would see it if you look that way. It would fill the sky. That would be an extreme case of this, that the further you go, the larger things look. Yeah.
Be analogous to the cosmic microwave background?
It is analogous to determining the curvature of space by looking at the cosmic microwave. But what are the things whose size you're able to decipher in the cosmic microwave background? And that is the size of certain acoustic lumps, but we'll come to that. And it's not galaxies. We don't look at galaxies in the microwave. We look at oscillating lumps of stuff, but basically it is the same. Okay, so there we have the three-sphere, and we discover what it means to an observer at the center of the universe. Where's the center of the universe? There is no center. But being very self-centered, we put ourselves at the center. We look out at different distances. We can also look at another thing. We can count the number of galaxies at different distances. It's obvious on a sphere that if you look out far, you see fewer galaxies than if you look the same distance on the plane. The plane sort of opens up, the sphere contracts. In fact, way out at the maximum distance, you basically have a chance of seeing one galaxy. Whereas at the same distance, in flat space, you would see a lot of galaxies. So counting galaxies is another way to tell. Counting galaxies, and you can figure out yourself how many galaxies you see at each radial distance on the sphere, and how many galaxies you see at each radial distance on the infinite flat space. Okay.
Excuse me. Help me here. So R, I shouldn't be thinking of R as getting very large. I should think of R as getting close to pi.
In the spherical case.
Yeah, so what does that, I mean, I'm trying to see what that means.
That's just a unit. That's just a unit. At the moment, I'm just telling you about the geometry of spheres. At the moment, we're not asking about increasing or decreasing or what made the sphere that size. We're just thinking about unit spheres. We might as well be thinking about unit spheres. Of course, if we thought of a sphere twice as big as a unit sphere, the same things would be true. But now we're just thinking about a world which is like the Earth, except it's three-dimensional, and it has a fixed known size. And it doesn't change with time. That's what we're talking about now. Now, of course, that's not really the case. Really the case, the world does change with time. It grows. But before we talk about the time dependence, we've talked now about two kinds of geometries which are homogeneous, meaning to say they're everywhere the same. There's a third. And the third has various names. I'm just going to call it the hyperbolic space. It's not as easy to imagine as the sphere. Oh, I'll tell you what, before we do that, let's talk about another way of representing the sphere. This will be handy when we go to think about the hyperbolic space. There's a way of thinking about spheres which is useful. We'll get some ideas from it. But more important is that it's a useful way of thinking about the hyperbolic geometry. All right, the sphere. It's called stereographic projection. A lot of you know what it is. You take the sphere, an ordinary space, and you rest it on an infinite plane. Mathematically, you're just passing a tangent plane through the south pole to a point on the sphere. This could be our point, the point where we are. Okay? Now, every point on the sphere can be labeled or mapped to a unique point on the plane. There's a little bit of trouble about the North Pole, but the North Pole is very far away. Let's not worry about it. Every point on the sphere can be identified with a point on the plane by so-called stereographic projection. You go to the North Pole and you take the point that you're interested in. Oh, incidentally, we are at the South Pole. We're at the South Pole, but that's not us. We're over here. We're at the South Pole. But here's what you do to stereographically project a point on the sphere. You draw a line, a straight line, through the point. It comes out, and it hits the plane somewheres. Here's another point. Hits the plane over here. Here's a point way up near the North Pole. That will map to some very, very distant point. Right? What about the point at the North Pole itself? Where does that go? It goes to infinity, and it doesn't matter what direction. Every point at the North Pole is out on a circle, a huge circle at infinity. You know, it's even nice not to think about points, but to think of little circles. Little circles, all, let's say, of the same size. They could stand for galaxies. Little circles all of the same size. By this projection, the circles on the sphere map to some kind of little closed curves on the plane. It's a little bit of magic, but circles map to circles. That's something you can prove if you have the patience for it. That if you take a little circle on the sphere and map it by mapping every point on the circle, you will find circles on the plane. That's obvious for the one at the South Pole. But what about the size of these circles? How does the size of the circles depend on how far up near the North Pole you are? Well, the answer is that circles of a given size near the South Pole look small, and not only small, they look about the actual size of the circle that they're mapping. As you move further and further, as the points move further and further, the circles up here look bigger and bigger. And in fact, the circle up near the North Pole here, the Arctic Circle, or the extreme Arctic Circle, that looks like a giant circle very, very far away. Okay? So that's a way to think about the sphere by mapping it onto the plane. And when it's mapped onto the plane, it has the bizarre properties that the further toward the North Pole you are, the bigger things look on the plane. But does that mean that the sphere is not homogeneous? No. This is just a way of drawing it. This is just a way of representing it. Every one of these circles is of the same intrinsic size on the sphere. Okay. So in mapping it to a plane like this so that you can draw it on a plane, you're distorting things. You can do the same thing with a three-sphere. You can also map it to an infinite flat three-dimensional space. Similar things happen. Spheres which are near you, map to small spheres. Spheres far away, map to bigger ones. So this is called stereographic projection. Okay. Now I'm going to tell you about the hyperbolic space. The hyperbolic space is made in exactly the same way. I'll take the case of the three-dimensional hyperbolic space, so we can do both, 3 and 2 dimensions. Yeah, let's start with 2 dimensions. Instead of calling it omega, we call it h. We call it dh squared. H stands for hyperbolic. dh squared, and now I'm talking about the 2-dimensional hyperbolic space. Exactly the same, dr squared plus something squared times d omega 1 squared.
dh squared or d?
Question?
dh or d omega?
dh2. The omega. I'll tell you in a minute. Okay. And here we put hyperbolic sine of r squared. Let me remind you what the hyperbolic sine is. Well, first let me remind you about ordinary sine. Sine of r is equal to e to the ir minus e to the minus ir divided by 2i. Everybody know that formula? That's the formula for sine in terms of complex exponentials. Hyperbolic sine is even easier. It's just e to the r minus e to the minus r over 2. In particular, hyperbolic sine for very large r is dominated by e to the r. E to the minus r is a very small number for large r. E to the plus r is a very big number. Sometimes I just call this sinh of r. It's a common term, hyperbolic sine sinh. Sinh of r is a function which grows very quickly. It grows exponentially. Sine, as you go far away, shrinks. As you go far away from r, sine shrinks back to 0. Hyperbolic sine just blows up and gets bigger and bigger rapidly, exponentially. So again, this is a space that when you look around you, you still see circles. We're still in lower dimension. We're still in 2 dimensions. You see around you a family of circles, but the size of the circles grows very rapidly. Blows up very, very rapidly. To go to the omega 3, to go to dh3 squared, which is the candidate geometry that we live in, a candidate, same thing. The r squared plus sinh squared r d omega 2 squared. Now we have the situation we're surrounded by two spheres, but the size of those 2 spheres gets really big really fast as we move away. What would you guess happens to the angle subtended by a galaxy as you go further and further away? Well, we can work it out. We can work it out in the hyperbolic geometry. Remember, the size, here we are. We're at the center. We're looking at a certain distance. We're looking at an object which has size d, intrinsic size d. It occupies an angle on the sky, d theta. Let's see what it is. We can replace the omega 1 squared as just d theta, or d theta squared. We have the size, the actual intrinsic size is d squared, and that should equal hyperbolic sine, or sinh of r squared, d, let's call it theta squared. The theta squared is the same as the omega 1 squared. Or just d theta, the size in the sky, is equal to d divided by sinh of r. Okay, now let's plug in what sinh of r is. For large r, when you look far away, we don't have to worry about this. For large r, it's just e to the r divided by 2. So if you plug that in, you find that d theta is approximately equal to d times 2 over e to the r. Now, e to the r grows very quickly as you go away. So what happens to this angle associated with a galaxy of size d as you go further and further away? It shrinks really fast. Furthermore, the number of galaxies grows especially fast. The number of galaxies grows very fast, and the size of them shrinks to match. So if you lived in the hyperbolic world and you looked out, you would notice that distant galaxies look too small. You don't have this phenomenon where after a point there's nothing left. It doesn't shrink back to 0. It keeps growing. But you would discover many, many more galaxies at a given distance as long as it's when it gets far away. You would find a huge increase in the number of them, and you would find each one of them anomalously small compared to flat space. So the geometries really have meaning. Okay, this is hyperbolic space. That's what this is. But I'll tell you how you get this picture. Okay. Yeah, somebody said, excuse me. You're excused. Go ahead. What do you want to ask?
Yeah.
Oh, maybe it was him. Yeah. He's excused.
I have a question.
Yeah.
So, although these equations all look kind of nice and, I don't know if symmetric is the right word, but similar.
They all look similar.
Yeah. In the case of positive, in the case of a sphere,
Positive curvature.
the interesting values
What's that?
of r are between 0 and pi.
Yeah.
In the case of hyperbolic space, the interesting values of 0 out to infinity.
Right. You got it.
Okay.
Okay. On the other hand, when we stereographically projected the sphere, it was onto the infinite plane. Now, of course, that was at the cost of an enormous distortion where things far away just look much too big. Okay? The opposite takes place on the hyperbolic plane. I'll show you a way to stereographically draw the hyperbolic plane. If a two-sphere, let's take the two-sphere case. I can't draw three-dimensional figures, especially when they're curved, so I'll stick with a two-dimensional case. Yeah. A two-dimensional sphere is x squared plus y squared plus z squared equals 1. Okay. I'm now going to draw a two-dimensional hyperbolic space. The two-dimensional hyperbolic space, again, you start with 3 coordinates. You could call them x, y, and z, but I'm going to call them x, y, and t, capital T. It's not really time. This is just a trick for drawing the space. It's not time. Nevertheless, I'm going to call it t. Take the x, y, xy t space, and construct not the sphere, but instead t squared minus x squared minus y squared equals 1. Instead of t squared plus x squared plus y squared equals 1, which would be a sphere, take t squared minus x squared minus y squared equals 1. Do you know what kind of surface this is? It's a no. With plus sign, it's a sphere. With plus sign, did somebody say a circle? It's a hyperboloid. If you only had one of these, it would be a hyperbola. With two of them, it becomes a hyperboloid. And here's what the hyperboloid looks like. Plot t upward, x and y horizontally. Oops, not so good over here. And now draw a cone. We're not really doing relativity, but it looks an awful lot like relativity. But this is just a trick for drawing a surface. Draw a cone. Whoops, that's not a very good cone. It's a right-angle cone, and it corresponds to the surface t squared minus x squared minus y squared equals what? For a cone. 0. T squared equals x squared plus y squared. That's a cone. It's not a hyperboloid. But now put a 1 there. Well, let's see. First of all, set x and y equals 0. Let's go on to the t-axis. Here's the vertical t-axis that corresponds to x and y equals 0. Where is the point t squared equals 1? Well, that's just a point t equals 1. There are two of them, one on the top and one on the bottom, but let's just concentrate on the top one. That's over here. T equals 1. What happens as you move away from that point? You form a hyperboloid. A hyperboloid of revolution. A round hyperboloid of revolution. Like so. Okay. Now, it does not look like every point on this hyperboloid is the same as every other point. It really looks like this one is special, but it's not. If you use the metric, not dt squared plus dx squared plus dy squared, but you measure distances on here as dt squared minus dx squared minus dy squared. Sorry, dx squared plus dy squared minus dt squared. You measure distances on here using the relativistic metric, pretending that this was time. It's not time. It's just an embedding space to draw a hyperboloid. If you do things that way, then this hyperboloid is absolutely uniform. How do I know it? Because to go from one point to another point on the hyperboloid is equivalent to a Lorentz transformation, which moves the time axis in various ways. But if you're not comfortable with that, we'll just take it as a true fact that the hyperboloid, when distances are measured with the metric dx squared plus dy squared minus dt squared, then this hyperboloid really is completely uniform. And now supposing I want to stereographically project it. Here's a way to stereographically project it that's useful. Again, you draw a tangent plane. A tangent plane now is tangent to the bottom point. Think of us as living at the bottom point here. We live at the bottom point, and we look out around us. We look out to given distances, distance out here, distance out here. But now we're going to take every point on the green hyperboloid and map it to a point on the blue plane. How do we do it? We just draw a line from the center over here to the particular point on the hyperboloid, and it intersects the plane somewheres. The point on the hyperboloid at the center, that just stays at the center. The point on the hyperboloid over here, I don't know, intersect somewhere over here. Oops, over here. Whatever. How about, how far out on this plane do you go? As you move out on the hyperboloid, you get closer and closer to the asymptotes of the hyperboloid here, but the asymptotes of the hyperboloid intersect the plane on a circle over here. So no point is ever mapped out beyond this circle. Even the asymptotically far away points, very, very far away, simply map to points near the boundary, near the circle here. So in doing this mapping, again, every point winds up in a particular place. That's good. But there's a lot of distortion. A lot of distortion, and in particular, things very, very far out there are squashed to very, very close to the edge of the circle. Things near the center, those are described pretty faithfully. Things out near the boundary are much too small. Quite the opposite, exactly the opposite of what happened when you took the sphere and spread it out on the plane. The sphere, you spread it out on the plane, everything far away was much too big. The hyperbolic geometry, things far away look much too small. But when you look at this picture, you're supposed to think in your mind that every angel and devil is exactly the same size as every other one. In fact, there are motions that you can do, coordinate transformations, that allow you to move the devils and angels around analogous to the rotation of a sphere. If you take the sphere and you rotate the sphere, the galaxies all move around. If you project them onto the plane, they'll appear to move all over the place. But really all you're doing is rotating the sphere. Same kinds of things here. They can all be thought of as the same size. Everyone sees exactly the same thing. If you look carefully, you'll see that every devil or angel essentially sees exactly the same features around him. And if you take into account that size scales have been deformed by this mapping, so that when you look at things, don't pay a lot of attention to the size, but do pay attention, for example, to how many angels and devils each one sees neighboring to him, you'll see that this really is homogeneous. Every point is exactly the same as every other point.
So this is sort of like the Penrose diagram in the sense that you're capturing everything in a finite.
It is like that. However, this is not a space-time. This is a pure space. This is pure space. Okay? Notice that as you look very, very far away, that things look very small, that the angle subtended by a very distant angel looks anomalously small compared to what would happen if they were spread out on the plane in a uniform way. Notice also that the number of them increases very dramatically as you move far away, increases exponentially. So that's I don't know, this geometry has various names. It's the Poincaré disk, the two-dimensional version of it. It's the Lobachevsky plane. It's the hyperbolic geometry. I'm sure it has other names. It's also the uniformly negatively curved space. The sphere is the uniformly positively curved space. And that actually means something technical. There's a certain components of the curvature which are really positive, and this geometry has the opposite sign for its curvature. So mathematically, it is the space of uniform negative curvature, and as I said, it's the same everywhere. Okay, so we have three kinds of spaces then. Oh, there's a three-dimensional version of this, and in three-dimensional version, instead of having a disk, you have a ball. You know what a ball is? A ball is the three-dimensional solid stuff contained within a sphere. A sphere always means the surface. Okay, that's a terminology. A sphere means the bounding surface. So when you say the Earth is a sphere, you're talking about the surface of the Earth. When you say the Earth is a ball, you're talking about everything contained within the bounding surface. Okay, so forgot why I mentioned that. Okay, I don't remember. So we have these three kinds of spaces. Let's write them down now. Oh, incidentally, just as the sphere has a natural radius, the hyperbolic geometry also has a radius. The radius is the thing which appears on the right-hand side, or the square, that's the square of the radius. This is the unit hyperboloid. It's the unit hyperboloid in that the center, the point over here is 1 unit away from the origin of coordinates. Just as you could also draw a sphere of radius 2, here's a sphere of radius 1, here's a sphere of radius 2. You can also draw a hyperboloid of radius 2. What you would do is just go up to 2 units here, and it would look like this. It would be somewhat flatter at the center over here. You draw a very big hyperboloid now would be much flatter, but it would be the same shape except expanded out uniformly, and you would indicate that by putting a radius of curvature in over here, some squared radius of curvature. All right, so the point is that each one of these geometries, in particular spheres and hyperbolic planes, hyperbolic disks, or hyperbolic balls, have a radius associated with them. And if you include the radius in their metric, if you want to think not about a unit geometry, then you just multiply the metric by the square of the radius. So let's do that now. Let's think about a sphere, ordinary sphere, the metric of an ordinary sphere of radius a, little a. A sphere of radius a, a unit sphere, has ds squared is equal to dr squared plus sine squared r, d theta squared, or d omega squared. Incidentally, in case I didn't mention it, there are 4 spheres, 5 spheres, 6 spheres, 7 spheres. In each case, if you want the 100-dimensional sphere, you write exactly the same formula, except you put the 99-dimensional sphere here. Always one less dimension around you than there are dimensions altogether. Okay, now supposing I want the sphere whose radius is not 1, but whose radius is little a. What do? I just multiply all sizes by a, and sizes squared get multiplied by a squared. A squared, little a squared. If the radius of my sphere, fixed radius of the sphere, is a, then the metric is exactly the same, except we multiply it by a squared. Okay. Here's the unit sphere, and here's the sphere of radius a, and we just multiply it up. Why a squared? Why not a? Well, because this is the square of a distance. What about the hyperbolic geometry? Same thing. ds squared is equal to a squared times dr squared plus hyperbolic sine squared r d omega squared. And that's the hyperbolic geometry of radius a. So we can not only accommodate unit spheres and unit hyperboloids, but arbitrary hyperboloids of arbitrary dimension. The bigger a, the flatter the hyperboloid is, but they're all similar to each other, similar in the technical sense that they're just expansions and contractions of the same thing. It is assumed in most of cosmology that the space that we live in is one of these three spaces. Let's take a 5-minute break. If you double the size of a sphere, what happens to its curvature?
Remains the same. Remains the same.
Not the way curvature is usually defined. Well, compare a basketball with the surface of the Earth. Which one would you say, if you explore around on it, looks more curved? Basketball. No. So the smaller the geometry, the higher its curvature.
Question?
Yeah.
You mentioned that that it's suspected that our cosmology is one of those one-up flat space.
Is what is?
You said that our cosmology is either spherical or hyperbolic. But
Or flat.
Or flat, okay.
Or something else. On scales out as far as can be detected, it looks flat.
Is it harder because the scale is so large?
Yeah.
To tell if it's curved one way or the other.
Right.
And the test is just those D measurements that you're talking about?
No.
Okay.
Well, if you only explore nearby, nearby means distances small by comparison with the radius of curvature, with the radius of the sphere, then you can't distinguish the three of them. They all look flat. Nearby. Yeah.
Can you say that if it's not flat, based on what we've seen, the universe has to be at least a certain minimum size?
Exactly. Right. The answer, we can see, literally, microwave, infrared, to what? I don't know, 20 billion light years or something like that, some number like that. Because it looks so flat out to that distance, we know that it is at least, at absolute minimum, 10 times larger in radius. Okay. That means 1,000 times larger in volume. Is it really just 10? Very, very unlikely, for reasons we will come to. Almost certainly much more than that.
Unless it's flat.
Well, flat corresponds to the limit of infinite, being infinitely big.
So there's no possibility of a finite but flat universe.
There is. There is. It could be toroidal, and maybe we'll talk about that, but no reason to believe it. Yeah. Yeah, there are other kinds of geometries. It's not that this is the only kind of geometry. In fact, there are even other, I said something not quite true. I said these were the only homogeneous geometries, but I was just reminded just now that that's not quite true. There are other geometries, namely the surface of a torus, the surface of a donut. Now, the surface of a donut does not look flat, okay? But that's only because you took the surface of the donut and tried to put it into three-dimensional space. I will tell you what a torus is. The surface of a donut. Mathematically, what a mathematician means by a torus. You start with a rectangle. Now let's first draw a torus. You know, the bagel. All right. The bagel has a property that its surface is two-dimensional, and you can move in two directions, and there are two independent ways that you can go around the torus and come back to the same point. You can go around it by starting out horizontally, and you'll come back to the same place. Or you can go vertically and come back to the same place. There are also other ways where you sort of spiral around as you go. You spiral one way as you go the other. But these are the two primary independent cycles on the torus. Okay? Now, you can represent the torus, at least the topology of the torus. When a mathematician speaks of a torus, they're usually speaking topologically. Take a rectangle and start walking on the rectangle horizontally. Let's use the same color coding. And you just come to the edge. But when you get to the edge, make an identification so that every point along the edge is identified as being identical with a point on the opposite edge over here. So that when you go out over here, you come here. You can go around it. You come back to the same place. That's the analog, or not the analog, but it's mathematically the same as going on the horizontal cycle here. You can also go on the vertical cycle if you remember to identify points on the upper boundary with points on the lower boundary. So you come around here. This point where the two cycles cross, that's just this point over here. All right. This is a torus. A rectangle with opposite sides identified is topologically a torus. It does have the property, first of all, it's flat. Why is it flat? Well, I just drew it flat on the blackboard. It's obviously flat. It's just a thing which I have drawn on the blackboard, on the flat blackboard. But it's periodic. It's periodic in two dimensions. It's doubly periodic, a mathematician would say. So it's topologically a torus, it is flat, and every point is the same as every other point. It doesn't really look like that. It looks like this point, being closer to the boundary, is different than the point in the center. But there is no boundary. There really is no boundary. You walk out here and you come over here. Every point is exactly the same as every other point, so it is also homogeneous. So when I said that there was only three possible geometries, I was being a little bit loose. There are others. Tori, plural of torus, is a particular case. But in many ways, you would just consider this flat. You'd consider it flat with periodic boundary conditions. Okay, so just to clarify this. Now, could we live on a torus? Yes, we could live on a torus, as long as the torus was big enough. If we lived on a small torus, we would notice it. We would look out and see our fannies from the other direction. Okay, in two different ways, we would see periodically. Okay, but as long as the torus was big enough, we couldn't tell. We couldn't tell the difference between it and flat space. So it's possible. It's not a popular idea. Oh, sorry, torus. Torus is a two-dimensional space, this torus. You can do the same exact thing in any number of dimensions. You make, instead of a rectangle, you make a rectangular parallelepiped, I believe it's called. And you do the same thing. When you come out this edge over here, you reappear here. In and out, you come out this end, you reappear at the other end, and so forth, up and down. So that's a three-dimensional torus. And you can have a torus of any number of dimensions. What's a one-dimensional torus? We started with a two-dimensional torus. I drew you a three-dimensional torus. What about a circle? Circle. Right. Or an omega 1. Okay.
Does anything new happen if a space is not simply connected?
like the torus. Yeah, there could, yes, it is possible that there would be, yes, as I said, you could look out in that direction and see your tail.
But you could do that on a sphere.
Different, it would be different, it would be different. The distortions would be different. Here there would be essentially no, yeah, it would be different though. You would have two directions in which you would see yourself, and other directions you would see something much more complicated. Yeah, you would, I'll tell you what you would think if you lived on the torus. It would be equivalent, it's completely equivalent to saying you live in flat space but with everything in the universe being repeated periodically. Here is U, here is U, same U, here is U, here is U. It's entirely equivalent because if you look out this side, you see, on the torus, you would look out and see yourself from the other side. Here, you look out and you see somebody who just looks exactly like you. So it's completely equivalent to saying that space is periodic and that you would just see replicas of the same thing in each rectangular cell. Would that be visible? Well, it depends on how big these cells are, but you know, you'd see yourself here, you'd see yourself here, you'd see yourself here, you'd see yourself up here. See like a crystal array of yourselves. You asked if there was anything different. That's pretty different.
So why is the sphere defined to end when you get to the other side, but the torus isn't?
Well, what else would you do with it? What else could you do with it? You could add another sphere on like that.
I was thinking you keep going around and you get the same periodicity. But
well, you have two spheres. How are you going to glue them together? A sphere is different than a torus. It's not really possible in a nice way to continue the sphere past pi. And the reason is because it shrinks, because the circles shrink to 0 at that point. The torus, when you go out to here, doesn't shrink to 0. It doesn't shrink away. Here, this thing shrinks away to 0 size as you move over to there. So it's not a nice prospect to pass through that point of 0 size. All right, let's go on now to space and time. Let's just review for a minute the metric of space-time. The metric of space-time in special relativity has two pieces, a time piece and a space piece. I'll just remind you what it looks like. Setting the speed of light equal to 1, ordinary Minkowski space, that's just flat space-time, special relativity, ds squared is equal to minus dt squared plus whatever, dx squared plus dy squared plus dz squared. Notice that the x squared plus dy squared plus dz squared is just the metric of flat space. So you've taken time and space and put them together, and as always in special relativity, the time component of the metric is negative, the space components of the metric are positive. If you wanted to ask how a light ray moves, how does a light ray move? What's the trajectory of a light ray? It's a trajectory in which ds is equal to 0. It's called a null ray. And what does that mean? Let's just have it move along the x-axis. Let's forget y and z. It would say that the t squared plus the x squared along the trajectory is equal to 0, or just that dt or dx is equal to plus or minus dt. dx equals plus or minus dt is just a light ray moving to the left with unit velocity or a light ray moving to the right with unit velocity. All right? So null rays. Light rays are null rays, meaning null here, standing for ds equals 0. All right. A more general kind of space-time, there's always time. In fact, there's always space. But we're going to deform or change the kind of space-time we're talking about, keeping time just as it is, but substituting for the three-dimensional flat plane here one of the three kinds of geometries that we've studied. One possibility is the plane, one possibility is the sphere, the other possibility is the hyperbolic geometry. But we're going to include one other thing, a scale factor. Let's take the case of the let's do two-sphere. Two-sphere just for visualization. dt squared plus d omega 2 squared. What is this? This is a world with time, but in which space is just a two-sphere. Here's space, the usual thing, and then there's time. That's all, space and time. But we're going to allow for the possibility that the radius of the two-sphere changes with time, and that's easily done. We just remember to change the radius of the sphere, we include an a squared, where a is the radius of the sphere, but now we allow a squared to depend on time, a of t squared. That's the cosmology of a world in which space is two-dimensional and in which the size of the universe, the radius of the universe, is time-dependent. Again, we can write down, if we like, how light rays move. Light rays, again, move along null directions. We'll work out some examples. Let's not do that right now. This is the space-time geometry of a world, two-dimensional world plus time. One speaks of 2 + 1 dimensional world. 2 + 1 means 2 dimensions of space, 1 dimension of time, with a time-dependent radius where space is a two-sphere. We can do the same thing for a three-dimension. And what does it look like? I mean, what it looks like is it's a basketball whose size changes with time. Okay, that's all. All right, you want a three-dimensional world? There it is. Same world. What about, take a pair of points. Take any pair of points on the sphere, separated by a given angular distance. Let's call that angular distance theta. What's the actual distance between the 2 points whose angular distance is theta? A theta. A is the radius of the sphere. A theta. Right, you got the right idea, you just got the wrong letter. All right, the distance between those 2 points is A, that's the radius of the sphere, times the angular distance. What's the velocity of the relative velocity of the 2 points? V equals A dot times theta. We're keeping the thetas of the 2 points fixed. We're keeping the 2 points fixed on the sphere, but just letting its radius change with time. What about the velocity as a function of distance? Velocity as a function of distance is A dot over A times distance. We've seen this formula before. This is the Hubble law, with A dot over A being the Hubble constant. Any 2 points on this expanding or contracting sphere, it doesn't matter, any 2 points, the velocity and distance between them, actual distance between them, satisfy the Hubble law with, as in the previous examples, the Hubble constant h is equal to a dot over a. So we're talking about something quite similar to what we talked about before. Notice that this fact doesn't depend very much on whether this was a two-sphere. It would also be true for a hyperboloid if we took 2 points fixed on the hyperboloid and allowed the hyperboloid radius to grow. Exactly the same thing would be true. In fact, if we took the flat plane and took 2 points at fixed coordinate distance, but allowed the coefficient here, a, to vary with time, we would still have the Hubble law. So let's write down the metric now of the 3 cases, the space-time metric of the 3 cases of interest. First of all, flat. ds squared is equal to minus dt squared. But this is not ordinary flat space-time. This is flat space, ordinary time, but with a growing geometry or a shrinking geometry. For that, we put here plus a of t squared. Let's say dx squared plus dy squared plus dz squared, or whatever, flat space. What this corresponds to is a flat world with a grid in it, a grid on it, the x, y, z grid. But exactly as we studied in Newtonian physics, we can imagine that the distance between neighboring points in the grid is changing as a function of time, like a of t. All right, so this is the geometry, the space-time geometry. This is the metric. This is the metric of the flat spatial universe with a scale factor which depends on time. Same thing is true if we took 2 galaxies fixed in the grid. The distance between them would increase with a, the velocity would depend on a dot, and the Hubble law would still be true. Okay. That's the flat geometry. And when I say flat, I mean flat space. How about the spherical geometry? That's ds squared, same thing, minus dt squared plus a of t squared. And now instead of writing a big thing, I'm just going to write d omega 3 squared. This d omega 3 squared stands for the metric of a 3-sphere, a unit 3-sphere, but the actual radius of the universe changes, a of t squared, excuse me. And what about the hyperbolic case? The hyperbolic case, same thing, ds squared equals minus dt squared plus a of t squared dh3 squared. All this means is that any fixed time, the geometry is either a sphere, a hyperboloid, or a flat space, but the scale of the space and the distance between galaxies embedded in the space, think of the galaxies as embedded in the space, that will change according to a and a dot. Okay, that's our cosmology. What do we need in order to make this cosmology have some dynamics to it? We need equations for how a changes with time. We're going to want to know, how does the universe, does it expand? Will it continue to expand? At what rate does it expand? Does it expand as t to the 2/3 or t to the 1/2 or exponential of t? What does it do? To do that, we have to have equations for how a changes with time. Now, we can't really use Newton's equations, although we will find the equations are Newton's equations. But we can't start with Newton's equations. We're talking about curved space-time now. We're really not talking about anything Newton would have written down. We're talking about geometries which are curved in both space, sometimes in space, but definitely in space-time, since a is changing with time. What are the rules for such geometries? The way the physics works, general relativity. So what we have to do is we have to write down the equations of general relativity for the special case of geometries which have this form, and they will translate, they will become equations of motion for a of t. we'll find there are three cases. Three cases depending on whether the world is flat, positively curved, or negatively curved. And those three cases we've already seen. Those three cases have the same equations as the Newtonian equations for positive energy, zero energy, and negative energy. The universe which is beyond the escape velocity, at the escape velocity, and below the escape velocity. So this is where we're going to go next. We will not spend a lot of time going through calculating all of the symbols in Einstein general relativity. I'll just sketch out for you the equations and what they lead to in terms of equations for A. The equations are simple. We've seen them before. They're the Friedmann equations. Once we have them and we know what they mean, we can explore the cosmology of them. Okay, good. Yeah.
Could the metric be tied up more complicated? In other words, here,
What's that, say it again?
dt squared, could ds squared be more complicated in the sense
Yes, of
that
course.
you have flat space, but you have time and space kind of.
Absolutely, yeah. You can certainly have more complicated cosmologies. And you might ask, why don't you include them? A lot of them will simply evolve into these. This is a natural sort of place that you would evolve to. But there's no question you can have more complicated cosmologies. These are the easy ones. These are the easy ones and the ones that are, let's call them popular. Yeah.
When we did the Newton version of the Hubble constant, we were talking about three-dimensional space, which is essentially wrong in your terminology.
We're still talking about three-dimensional space.
So the spheres are the boundaries, essentially?
No, we're talking about a three-sphere. A three-sphere is a three-dimensional space. It's not the boundary of anything. It is space. You've got to learn to stop visualizing the sphere as a thing which is embedded in higher dimensions. You've got to think only of the spherical surface, or in three dimensions, one more dimension. This is hard to do. Your mind does not want to visualize the three-sphere. So the only way to visualize it is through the equations for it. But it's not embedded in a higher dimensional space that you can move off the surface and onto the surface. It is just, it is, that's all. Okay.
One question?
Yeah.
Is luminosity our only observation for distant galaxies,
No.
for the distance of galaxies?
No, no, no. There's a whole range of different. One way is to use the Hubble law to relate distance to velocity, and then measure the velocity by the redshift, by the Doppler shift of spectral lines. Other ways which are useful is knowledge of the, well, this is luminosity of particular kinds of galaxies. Supernova. Right. Supernova have definite absolute luminosities, and from the absolute luminosity, but that is using luminosity.
What I'm thinking is that for luminosity, if we're assuming the luminosity is inverse square, we're implicitly assuming that the space is flat.
Well, that's the easiest case. You do your combination of measuring luminosity, measuring redshifts, measuring spectral lines, taking into account the possible different possibilities for expansion of the universe, whether it's positively curved, negatively curved. Take them all into account, measure all of them, and you get a sort of composite. Right. But, you know, to say it simply, as long as space is approximately flat over a big enough region, use luminosity to determine the distance is the easiest way to think about it. But there are other ways.
I would think that the luminosity, if the space were curved, the actual luminosity observed would not be inverse square, and that would cancel out the other effects of the curvature. So even if we're in a hyperbolic space, it may look flat if we're just basing observations on that and the size.
No. All of this gets taken into account. And, you know, experts do it. They keep track of everything. Big computer codes, and what you say is right. But
Today, essentially, all of the data that you cross-correlate agrees with a flat space model. Today, all the data that you cross-correlate with these different measurements agrees with a flat space model.
to about 1%. 1% means that the curvature is 0 to within about 1%. That translates into the statement that the universe is at least 10 times bigger than the visible region. Okay.
For more, please visit us at stanford.edu.